Hello there, and welcome to the Sleepless Scientist, a calm corner of the night where science drifts slowly and curiosity hums like a distant star. Tonight's journey isn't a story from deep history or far theory, but something happening right now. Somewhere beyond the sun, a faint blue light is moving closer, a visitor from between the stars. Its name is 3I Atlas, the third confirmed interstellar object ever seen passing through our solar system. It was first spotted on July 1st, 2025 by the Atlas Telescope network in Hawaii. And since then, astronomers have realised that this traveller doesn't quite behave like anything we've seen before. You could think of interstellar objects as cosmic drifters. They're stones, or maybe icy fragments, that once belonged to other star systems, tossed into the dark millions or billions of years ago and left wandering the space between suns. Occasionally, by a near miracle of timing and geometry, one crosses the path of our own solar system. The first we ever found was 1I Oumuamua in 2017, a strange cigar-shaped object that seemed to accelerate without reason. Then came 2I Borisov in 2019, a more ordinary comet, but with exotic chemistry that told of a different birthplace. And now 3I Atlas, smaller, faster, and somehow more puzzling than both. When astronomers first traced its motion, they noticed something uncanny. The object was racing through space at about 58 kilometers per second relative to the Sun. That's fast enough to cross the United States in less than a minute. Too fast to have formed here, too free to ever be captured again. Its path wasn't an ellipse like a planet's orbit, but a stretched open curve, what scientists call a hyperbola, meaning it will visit once and then slip away forever. Even more surprising, that path lies almost perfectly flat along the plane of our solar system, tilted by only about 3 degrees. It's as if a skipping stone from another ocean happened to glide exactly across the surface of ours. Where did it come from? The best reconstructions trace its incoming direction back toward the centre of our galaxy, toward the dense star fields of Sagittarius A star, the Milky Way's heart. That doesn't mean it was launched from there, but its trajectory aligns with the general motion of the thick disk of older stars, suggesting the material that made it could be over 7 billion years old. Imagine an ancient shard of ice and dust that has been coasting between suns since before Earth itself had oceans. From the start, Atlas looked different. Even when it was still far from the Sun, well beyond the orbit of Jupiter, telescopes noticed a faint haze forming around it. Most comets stay frozen and silent until they come much closer, when sunlight warms their ice into vapour. But Atlas began to glow early, as though some of its materials were more eager to breathe. Later, space telescopes like TESS and JWST confirmed something remarkable. Its cloud of gas contained far more carbon dioxide than water, about 8 parts to 1. On Earth, we'd call that a reversed recipe. Usually water dominates. Here it was the faint hiss of dry ice that led the dance. If you were close enough to see it, you might have noticed its light behaving strangely too. It scattered sunlight in a way that gave off an unusually deep, negative polarization, a technical phrase meaning the reflected light waves were tilted backward, like the echo of a whisper instead of the voice itself. That told scientists its surface grains were structured in a peculiar way, maybe porous, maybe smooth like glassy frost, and even its dust tail seemed to defy convention, pointing not away from the sun but slightly toward it, driven by faint jets of carbon dioxide. Everything about Atlas whispered, not impossible, but unexpected. At this stage, most astronomers simply nodded in fascination. Nature has a long history of surprising us, and a unique comet isn't cause for panic. It's cause for new models, new data, and better understanding of how icy bodies behave when they come from colder, older places than our own. But even in that calm observation, one fact lingered. This object was already active, already changing, long before it entered the realm where sunlight could stir it. Whatever Atlas was made of, it carried memories of environments colder and stranger than anything nearby. And so, through the summer of 2025, telescopes around the world began to track it more closely. Each night's observations showed it moving steadily, its blue-white hue slowly deepening. Scientists predicted its closest pass to the Sun, its perihelion, would occur on October 29th, 2025, at about 1 1/3 the Earth-Sun distance. After that, it would head back outward, crossing Earth's orbital path and coming nearest to us on December 19th, 2025, about 9 million kilometers away. That's safely distant, yet near enough for the most detailed study ever of a visitor from another star. In the quiet rhythm of scientific reporting, there's a certain poetry that hides between the numbers. 58 kilometers per second isn't just speed. It's a story of momentum preserved over cosmic ages. 3 degrees of tilt isn't just geometry. It's a coincidence of planes that makes this one brief encounter possible. And when we say 7 billion years old, we're really saying that this little traveller has seen suns ignite and die, has wandered longer than all of human history combined. Whether 3I Atlas turns out to be an ordinary comet with extraordinary chemistry, or something entirely unexpected, it's already doing what every good discovery does, reminding us how small we are and how easily wonder returns when we simply look up. For now, it's still far away, drifting in the deep sunlight between orbits, a tiny dot of cobalt blue against the dark, but in the months to come, as it swings closer, it may offer answers, or perhaps only more gentle questions about how much the universe still has left to show. So, let's follow it together. From its first shimmer in the data to its bright turning near the sun, and on toward the quiet December when it will pass us by. The sky has sent us a messenger, ancient, beautiful, and maybe, in some way, aware of our gaze. And as the Earth spins through another night, we listen, softly, for what this blue traveller might be trying to tell us. If you close your eyes for a moment, imagine our solar system as a small garden surrounded by the endless plain of the galaxy. Most of what drifts through this garden, asteroids, comets, dust, is born from within it. But every so often, something unfamiliar wanders in. A seed from another field, a pebble from another shore. These are the interstellar visitors. In all of human history, we've only met 3. The first arrived quietly in 2017. Astronomers at Haleakala Observatory in Hawaii noticed a slender object streaking across the sky faster than anything they had ever tracked. They called it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was small, barely 100 meters long and strangely shaped, like a shard of polished stone, or perhaps a pancake turned on its edge. It showed no tail, no visible gases, yet it moved as though something unseen was gently pushing it. Some thought sunlight itself could be propelling it, as if it were a natural light sail. Others whispered that maybe it wasn't natural at all. Whatever the truth, Oumuamua slipped past the sun, looped once, and sailed out of our reach, its speed too high to ever return. 2 years later came 2I Borisov, discovered by an amateur astronomer in Crimea. Unlike the first visitor, Borisov looked every bit the classic comet, streaming dust glowing faintly green, venting cyanide and carbon monoxide. But it was chemically different from any comet born near our sun. Its ratios of gases, its dust particles, even the way it broke apart before leaving, all suggested a chemistry older, colder and harsher than our own neighbourhood could produce. It was the first time scientists could truly say, this is a piece of another planetary system passing through ours. Then, in mid-2025, came the third. 3I Atlas, named for the telescope network that first caught sight of it on July 1st. At first glance, it was just another dim, moving dot. But then came the calculations. A speed of nearly 58 kilometers per second relative to the Sun. So fast that nothing born here could have achieved it. The shape of its orbit wasn't an oval, but a curve that opened endlessly outward, what astronomers call a hyperbola. In simple words, it's a one-time visitor destined never to come back. And even more curious, its path runs almost exactly along the same flat plane as all the planets, the ecliptic, tilted only about 3 degrees. Imagine tossing a pebble into a spinning disk and watching it skim perfectly across the surface without touching. The odds of that geometry happening by chance are astonishingly small. The numbers told another story too. When researchers traced its course backward through space, the trail seemed to point toward the dense heart of the Milky Way, the region around Sagittarius A, where stars swarm thickly around the galaxy's central black hole. No one can say it truly came from there. The galaxy is too vast and gravity too tangled to know exactly. But its motion matches the older population of stars known as the thick disk, a layer of ancient suns billions of years senior to our own. That means the rock or ice that formed 3I Atlas could be more than 7 billion years old, a relic from an earlier generation of worlds. It's easy to forget how enormous those numbers really are. 7 billion years ago, the Earth didn't yet exist. The sun was still gathering its halo of dust. Somewhere, far away, another star may have had planets orbiting it, and around one of those planets circled a moon or an icy body, quietly waiting for some disturbance, a passing star, a gravitational twitch, to fling it loose into the dark. And from that moment on, it began its voyage through interstellar space, travelling for ages upon ages, until now. That journey is almost beyond imagination. Between stars there is no air, no light, only an ocean of dust grains and radiation so thin that a single particle might travel hundreds of kilometres before meeting another. Yet in that emptiness, Atlas survived. Its surface was sandblasted by cosmic rays, its molecules rearranged by time, its edges darkened by radiation. For billions of years it drifted, until one day the gravity of our sun reached out across the void and caught it in a faint one-time curve. Now, after all those years alone, it's passing through our garden. Scientists like to name things carefully. The 3I in its name simply means third interstellar, a quiet reminder that such encounters are still unimaginably rare. Each one has given us a glimpse of something new. Oumuamua taught us that interstellar objects can be rocky, small, and mysterious. Borisov showed that they can also be full of ices and gases, like comets from alien systems. And now Atlas seems to be a mixture of both, dusty yet vivid, structured yet unpredictable. The first observations from telescopes like JWST, TESS, and Sphere-X deepened that curiosity. The light from Atlas was a soft bluish white, rather than the warmer tone of ordinary comets. Its spectral fingerprint revealed an unusual abundance of carbon dioxide, far more than water vapour. Normally, in comets near our Sun, the opposite is true. Frozen water dominates, and carbon dioxide is only a trace. But in Atlas, the ratio was flipped, roughly 8 parts carbon dioxide to 1 part water. That's like finding a snowball that steams before it melts, exhaling cold vapour long before warmth should reach it. It began outgassing even when it was 5 times farther from the Sun than Earth, well beyond the point where sunlight could usually cause such activity. Whatever it's made of, its materials are far more volatile, far more eager to sublimate than anything we've catalogued. And then there's its colour. As the sunlight scattered through its dust and gas, the polarisation of that light behaved strangely. Tilted, inverted, what researchers called extreme negative polarisation. The phrase sounds clinical, but what it means is simple. The light waves that bounced from its surface didn't follow the usual direction. They seemed to twist back like ripples rebounding off a hidden wall. That told astronomers its surface grains were somehow different, perhaps smoother, perhaps structured like microscopic glass spheres instead of jagged ice. All of these clues, its speed, its path, its chemistry, point to a single truth. Atlas isn't just from another place, it's from another time. Each observation peels back a little of its story, a fragment forged in the birth of some forgotten star system, wandering across light years, arriving here by chance, or perhaps by the quiet pull of physics we're only beginning to understand. For most people, these facts don't feel immediate. The numbers, 58 kilometers per second, 3 degrees of tilt, 7 billion years, sound remote, abstract. But if you let your imagination soften them, they become images you can almost see. A traveller skimming across the vastness, brushing the edge of our spinning world. A piece of ice breathing out gas before it even feels the sun. A shard of another dawn, polished by the silence of interstellar space. As scientists tracked its approach through the summer and into the early autumn of 2025, they could already sense it would be special. Its brightness curve was rising faster than expected, its coma expanding even before the main event, the moment it would swing closest to the sun. Something unusual was stirring, and though no one could say exactly what, there was the quiet thrill that always comes before discovery. Because every time we find a new traveller like this, the universe gives us another small reminder. We're not a closed story. We're part of a much larger conversation, one that began long before us and will go on long after we're gone. And somewhere out there, between the stars, more of these messengers are still on their way. Tiny sparks crossing the dark, waiting for a moment to shine. When the first faint points of light from 3i Atlas appeared in telescope images, they looked like nothing more than a smudge against a background of stars. But within that small blur, something strange was already unfolding. Even from 5 times farther out than the Earth is from the Sun, this traveller was awake. Its coma, the soft halo of gas that forms when a comet warms, had begun to bloom too soon, as if it couldn't wait to announce its presence. Normally a comet remains asleep until sunlight grows strong enough to heat its frozen water. Only then does the ice begin to vaporize, carrying dust along with it. But Atlas began exhaling while it was still in the deep cold of space, beyond Jupiter's orbit, where sunlight is so faint it's closer to twilight than day. The simplest explanation is that Atlas isn't built like the comets we know. Its ice isn't mostly water, but something far more restless: carbon dioxide and carbon monoxide, gases that sublimate even in gentle warmth. In its chemical recipe, the ratio of carbon dioxide to water was roughly 8:1. If you could hold a piece of it in your hand, though that would be unwise, it would fizz like dry ice in a warm room, hissing away before you even felt it melt. This early activity told astronomers something about its birthplace. It must have come from a region of its original star system so cold that even carbon dioxide could freeze solid. A world of dim light, where frost would collect like smoke on rock, where ice might form in layers as delicate as lace. There, deep in that ancient darkness, this comet was built, and when some distant gravitational encounter finally hurled it into interstellar space, those fragile layers came along for the ride. After billions of years adrift, they still remembered the cold that shaped them. From May through August of 2025, observatories turned their eyes toward it. TESS, the transiting exoplanet survey satellite, first caught the flicker, barely perceptible variations in brightness that suggested rotation. Then the James Webb Space Telescope joined in, reading the heat signature of its gases. SPHEREX, a mission designed to map cosmic chemistry, detected the same pattern: bright bands of carbon dioxide with only traces of water and methane. Together they built a picture of a comet made mostly of exotic ice, something like a soda glacier from another world. But there was another surprise waiting in the light. When the glow of Atlas was analysed, its polarization behaved oddly. Usually when sunlight scatters off dust, the electric field of that light tilts in predictable ways. Atlas tilted it the opposite direction, what scientists call extreme negative polarization. In simpler words, the reflected light was whispering back instead of shouting out. It's the optical equivalent of an echo returning upside down. This told researchers that the surface of its dust grains might be unnaturally smooth or organised, not the random jumble found in ordinary comets. Some wondered if its grains could even be sintered glass, tiny spheres forged by cosmic radiation during its endless drift between the stars. It's tempting to see these details as coincidences, as quirks of physics, and yet, when patterns stack one atop another, even cautious minds begin to lean forward. Carbon dioxide dominance, premature activity, reversed polarization, and almost perfect alignment with the ecliptic. Altogether, they form a constellation of oddities. None impossible on their own, but together, undeniably strange. At observatories in both hemispheres, astronomers began to share late-night messages, half in excitement, half in disbelief. There was talk of supervolatiles, of ancient ices, of hyperactive comas, words that sound like poetry but are, in their way, perfectly technical. And quietly, without fanfare, a few also began to ask a softer question. What if these anomalies aren't just chemical? What if they're structural? Could the body of Atlas be hollow? Could it contain cavities or shapes that influence how sunlight warms it, how it vents gas, how it spins? No one said the word artificial, not yet. But history shows how quickly imagination stirs when the unknown enters our sky. Back in 2017, when Oumuamua flashed by, its odd acceleration led to months of speculation, everything from alien probes to shards of shattered planets. The lesson then was clear: extraordinary claims need extraordinary evidence. So this time, the community moved with care. Instruments were recalibrated, data checked twice, then checked again by teams half a world apart. The strangeness, however, refused to vanish. Each week, Atlas grew brighter. By September, its light curve showed steady pulses, as if its rotation was uneven, wobbling slightly. That might simply mean its shape was irregular, with jets of gas pushing it unevenly. But when scientists plotted the intervals between bright and dim phases, they noticed something peculiar. The timing followed a ratio eerily close to the Fibonacci sequence, those numbers that spiral through sunflowers and seashells. Was it coincidence? Probably. Nature is full of spirals. Still, it added a hint of rhythm to what was already a symphony of anomalies. By now, the comet's path was well mapped. It was rushing inward toward its closest approach to the Sun, moving along a line almost perfectly parallel to the orbits of Earth and Venus. In December, it would pass about 9 million kilometers from Earth. Safe, but close enough to study in detail. That distance sounds vast, but in cosmic terms it's a handshake. A single day of Earth's orbit would carry us farther than that. For astronomers, it meant the best observing opportunity in decades. As the months passed, telescopes began to see subtle changes in colour. The faint blue tone deepened, not as a trick of sensors, but as real physics. Molecules of carbon monoxide and cyanide fluorescing under ultraviolet sunlight. The comet's halo thickened, curling into soft plumes. Against the black of space, it would have looked like a tiny glowing ember wrapped in its own mist. Through all this, the scientific tone remained steady. Observers logged their data in daily bulletins. The International Astronomical Union updated orbital parameters. Each report ended the same way. Further observations encouraged. Behind those words, though, you could sense the quiet excitement of discovery. It's not every year, or even every century, that something from another star drifts close enough to touch our instruments, to test our understanding of what's possible. And so, by late October, when Atlas approached the inner solar system, the stage was set. Ground telescopes, space telescopes, and even spacecraft designed for solar monitoring were ready to watch its passage. No one could predict what would happen next. Some expected it to brighten gently, to peak and fade like a normal comet. Others, remembering Oumuamua, wondered if it might do something no one had planned for. But the sky has its own timing. On the edge of October, just as the sun grew restless with flares, Atlas prepared to reveal its greatest secret yet, a flash so bright, so blue, and so brief that it would leave even the most measured scientists staring in quiet disbelief. And from that moment on, 3i Atlas would no longer be just a curiosity from another system. It would become a mystery for ours. By the time 3i Atlas crossed the orbit of Jupiter, it was already shedding light and vapour like a small glowing ember. For a comet, that kind of eagerness is almost unheard of. Most of them remain still and silent until they are much closer to the sun, as if asleep under layers of frost. But this visitor had begun to stir early, whispering its presence from a distance where sunlight is weak and cold. To astronomers watching from Earth, it was like seeing a candle flicker inside a cave long before anyone had struck a match. That early awakening puzzled everyone. The numbers simply didn't fit the familiar pattern. At 5 astronomical units away, about 5 times the distance from Earth to the Sun, the solar warmth should have been too faint to melt even the most delicate ice. Yet there it was, a faint mist unfolding around it, already alive. Scientists suspected that this was not an ordinary blend of water and dust. Its frozen material must be made of gases far more restless than water, carbon dioxide and carbon monoxide, which can escape into vapour even in the outer chill. In simpler terms, it was as though this comet had lungs that exhaled at the first hint of dawn. When astronomers measured the gases in that vapour, they found a pattern no one had seen before. The balance between carbon dioxide and water was reversed. Instead of the usual mix where water dominates, Atlas contained roughly 8 parts carbon dioxide to every single part of frozen water. On paper, that's a small difference in numbers. In the language of chemistry, it's astonishing. It means that what should have been an icy snowball was more like a stone of dry ice, fizzing softly as the sunlight touched it. Imagine holding a handful of snow that steams like breath instead of melting into water, each grain releasing a ghostly cloud as it warms. This inverted chemistry told a story of where Atlas might have been born. Somewhere far colder than the outer edges of our solar system, perhaps in the frozen outskirts of another star, where the light is so weak that even carbon dioxide freezes solid. A world of shadow and slow motion, where time moves like molasses and frost forms in the dark. There, in that ancient silence, Atlas was built grain by grain, ice layered upon ice, until some gravitational tremor sent it flying outward, never to return. For billions of years it drifted in that emptiness, untouched, until now. But the oddities did not end there. The light that reflected from its dust behaved as strangely as its chemistry. Most comets scatter sunlight in a predictable way, the brightness polarized along certain directions. Atlas, however, bent those rules. The waves of light came back tilted the opposite way, what scientists call negative polarization, a term that sounds complex but simply means the light was reversed, like a mirror reflecting from its own shadow. In human language, it was as though the comet's glow whispered instead of sang. This kind of light behaviour suggested that the particles surrounding it were shaped differently from the rough, irregular grains we know. They might be smooth, perhaps even glassy, formed when cosmic radiation fused their outer layers during their long interstellar drift. Under a microscope, if one could somehow collect them, they might look like tiny spheres of translucent smoke, the fossilized breath of ancient starlight. Such details are easy to miss in the noise of scientific reports, but for those who track these faint signals, each small anomaly feels like the pulse of something deeper. Early outgassing, reversed polarization, reversed chemistry. The list was growing. One anomaly could be dismissed as coincidence, 2 as curiosity, but 3 began to form a pattern. And patterns, even faint ones, have always been the astronomer's music. Among the more poetic possibilities was the thought that Atlas could be hollow inside, a fragile lattice or porous sponge of ice, allowing sunlight to seep deeper than expected, warming it from within. In that case, gas might have found paths to escape even at great distance, creating jets that turned on and off as the comet spun. Another idea proposed that it carried long-buried volatile pockets left over from its violent birth in another solar nursery. Each theory added another brushstroke to the picture, a cold traveller, built from unfamiliar materials, breathing unevenly as it crosses a foreign sun. Observatories around the world began to track its rhythm night after night. The object seemed to brighten and dim in cycles, as though turning its face toward and away from us. This rhythm wasn't perfectly regular, but it had a kind of organic pulse. When plotted on graphs, the changes followed a pattern that reminded many scientists of the Fibonacci ratios found in natural spirals 1, 2, 3, 5, 8, 13. A quiet repetition that shapes the curves of shells and sunflowers. Whether this was coincidence or just the brain's fondness for recognizing order, no one could say. But it added a note of wonder to what was already a remarkable find. Meanwhile, the comet's tail began to form, except that, at first, it pointed in the wrong direction. Instead of streaming away from the sun, it curved slightly toward it, forming what astronomers call an anti-tail. The cause lay in a subtle dance of forces. The jets of carbon dioxide gas, combined with a weak solar wind at that distance, pushed fine particles backward along the orbit, creating the illusion of a tail that defied expectation. To the eye, it might have looked like a thin brushstroke of light stretching sunward, as if the comet were reaching back toward the star rather than fleeing from it. All of these details added up to an image that was both scientific and strangely human. Here was an object from another world, behaving with a kind of personality, impulsive, unpredictable, glowing blue before it should, turning its face toward the sun like a restless dreamer who can't sleep. And yet, every strange behaviour was still within the laws of physics, just pushed to their quiet edges. Nothing supernatural, only natural in a way we hadn't seen before. As weeks passed and the comet drew closer, anticipation grew. Astronomers adjusted exposure times, tuned instruments, and shared data across continents. Space telescopes like SOHO and Stereo prepared to watch it near the sun, while ground-based arrays waited for its return to evening skies. The moment of closest approach to the sun, its perihelion, was approaching. Predictions varied. Some thought it would brighten gently and fade, others expected an outburst. The truth, as always, would be decided by the object itself. In the calm before that event, the early months of observation had already changed how we thought about interstellar visitors. Atlas had proven that there are more ways to build a comet than we ever imagined. It showed that even after centuries of studying the heavens, the universe can still hand us something that doesn't fit the chart. It was a small blue reminder that mystery is not a flaw in our knowledge. It is its heartbeat. Somewhere in that glowing breath of carbon dioxide, in that shimmering halo of dust and ice, lies the record of another sun's infancy. And as it drifts toward ours, it carries that story across the abyss, unread but unbroken. In a few weeks, when it brushes closest to the sun, that record will flare, briefly, into light, and for a moment, all of humanity will be watching. When the first detailed spectra of 3I Atlas arrived from the James Webb Space Telescope and ground-based observatories, the scientists expected to see the usual suspects. A comet's light, when spread out into its rainbow of wavelengths, is like a barcode of its ingredients, each element leaving its own delicate fingerprint. In nearly every comet we've ever observed, one of those fingerprints belongs to iron and another to nickel. They usually appear together, bound by chemistry and origin. But in Atlas, something extraordinary appeared. The nickel was there, gleaming in sharp emission lines, but the iron was missing. It's a small sentence, nickel without iron, but it carries the weight of astonishment. In the history of cometary science, this pairing has been as consistent as salt and water. Both metals condense in similar environments. They're born from the same temperatures in the disks that form around young stars. To find one without the other suggests something strange about where this object came from, or how it was made. Nickel is heavier than most elements found in comets, and for it to vaporize into gas requires heat. Far more heat than sunlight alone could provide at the distance Atlas was observed. Yet there it was, shimmering in the data, a quiet thread of metal glowing in ultraviolet light. One explanation is that tiny grains of pure nickel were being freed from the comet's surface by jets of carbon dioxide, exposed briefly to sunlight and then ionized, giving off that spectral glow. Another possibility, more exotic, is that the comet's surface had already been altered long ago by cosmic radiation, forming an alloy that separated the metals. Over billions of years of interstellar travel, lighter materials could have been eroded away, leaving only the dense nickel structure behind. But to some observers, it felt almost too perfect. Nickel is a useful metal, strong, resistant to corrosion, magnetic. To find it shining alone on an object that had already shown signs of symmetry and rhythm made imagination stir. Could this be a coincidence? Or was there something about Atlas that had been crafted, or refined, rather than formed? Caution ruled the discussion. The astronomers who first released the results made sure to underline the natural explanations first. Perhaps iron was present but hidden, bound in compounds that didn't emit at the same wavelengths, or trapped deeper within the nucleus where sunlight couldn't reach. Instruments can be fooled by calibration errors or background noise, yet after repeated measurements the pattern remained. The nickel lines stood out bright and clean, like threads of silver light against a dark cloth, while the iron lines stayed silent. To explain it gently, imagine you were listening to an orchestra where two instruments always play together, say a violin and a cello, but one night you hear only the cello. You might wonder if the violinist is merely playing softly, or if they didn't come at all. That's how it felt for those reading the spectra of 3I Atlas. The familiar duet of nickel and iron had become a solo. This metallic anomaly fits neatly into the growing list of the comet's peculiarities: its early outgassing, its reversed chemistry, its reversed polarization, all now joined by a composition that seemed partly refined. The word refined isn't casual here. On Earth, separating nickel from iron is not easy. It takes industrial processes, heat and time. Nature can do it too through repeated cycles of melting and freezing in the violent environments around new stars. But in this case, Atlas's apparent purity was so unusual that researchers began to ask whether it might have experienced conditions unlike any natural object we know. If it came from a star system very different from ours, one richer in nickel, or one whose inner worlds were hotter, that could explain much. But there was also the faint possibility that the object had been part of something else, a larger body, perhaps a planet's core fragment, thrown into space after a collision. That would make it less a comet and more a shard of a lost world. If so, then the story of Atlas becomes even more haunting. Not a wanderer born in the cold, but a relic of some long-ruined planet, drifting among the stars for eons before crossing paths with ours. Even its behaviour supported this strange duality. Most comets are dirty snowballs, fragile, full of volatile gases and dust that scatter easily. Atlas, however, appeared oddly cohesive. When jets erupted from its surface, they didn't seem to tear it apart or make it spin wildly. It was as though the body beneath the vapour had a certain sturdiness, a backbone. This strength could be due to dense metal content, or, to indulge a gentler curiosity, a structure built for endurance. At the same time, the light from Atlas kept shifting in tone. Its brightness fluctuated slightly every few hours, revealing that it was rotating. By mapping those pulses, astronomers estimated a spin period, roughly one full rotation every few hours, though it changed subtly with time. This was another small mystery. The changes followed a repeating rhythm, once again echoing those familiar Fibonacci-like intervals. Natural or not, the pattern was hypnotic. Nature, after all, is not shy about spirals. They appear in everything from galaxies to pine cones. But when that spiral shows up in light curves and radio echoes, even the most skeptical mind pauses for a moment. To bring all this down to simpler imagery, Atlas behaved like a snowball laced with wires of metal, spinning in sunlight, venting faint blue gas from hidden seams. Its chemistry spoke of another star, its motion of a long journey, its light of a structure unlike any cometary object we know. Whether those seams were natural fractures or something more deliberate, only time and close observation could tell. In science, mystery is never an endpoint. It's an invitation to keep looking. For every person dreaming of alien probes, there are hundreds running data through models, checking each instrument, comparing signals from different observatories. Wonder and rigor go hand in hand, and Atlas was generous enough to offer both: wonder for the dreamers, data for the patient. By early October, the object had become one of the brightest interstellar bodies ever observed, still months from its closest approach. Its gas jets had grown, forming a faint envelope around a compact core that shone steadily. The nickel emission lines continued to glint faintly, while the rest of its spectrum stayed strangely calm. The idea of an engineered object remained unproven, whispered more by the public than the professionals, yet even the professionals couldn't hide a quiet fascination. Because sometimes, even when the explanation is natural, the beauty of that nature is so intricate that it feels designed. And so, as 3i Atlas drew closer to the Sun, the world waited for its next act. Was this metallic glimmer just a fleeting trick of physics, or the first sign of something we'd never seen before? Whatever the answer, it reminded everyone who watched the night skies that discovery is never about certainty. It's about paying attention to every unexpected note, to every missing violin in the cosmic symphony. As October unfolded, 3i Atlas reached the heart of its long journey, the moment when it would pass nearest to the Sun. Astronomers call this point the perihelion, from an old Greek word meaning near the Sun. For Atlas, that distance was about 1 1/3 times the gap between Earth and the Sun, roughly 200 million kilometers. It sounds far, but in the scale of space, it was close enough for sunlight to strike it with full intensity. And that was when the quiet, icy visitor did something no one expected. For several days before perihelion, the comet's behaviour had been calm. Its brightness rose slowly, matching models that predicted a modest outburst. But on October 29th, just as it slipped behind the Sun from Earth's point of view, it began to flare. Spacecraft positioned around the Sun, SOHO, Stereo A and GOES 19, caught the moment in their cameras. The images showed a burst of light expanding outward like a faint blue halo. Within hours, Atlas had brightened by a factor of hundreds. Its surrounding envelope of gas swelled until it reached nearly 300,000 kilometers across, 25 times the diameter of the Earth. In ordinary comets, brightness grows according to distance, following a gentle mathematical rule. Light intensity increases as the square of the closeness to the Sun. But Atlas defied that expectation. Its brightness followed a steeper curve, nearly 7 times stronger than normal. Astronomers described it in their reports as brightness proportional to distance to the power of -7.5. But to imagine it more simply, think of it as a lamp that grows tenfold brighter each time you take a single step nearer, until suddenly it becomes almost blinding. And then there was the colour. Instead of the usual yellow-white glow of most comets, Atlas blazed blue, not the pale turquoise sometimes seen from ionized gases, but a deeper, purer hue, richer than the sky itself. For the first time in recorded history, a comet had become bluer than the sun's own light. Every instrument that measured it, spectrometers aboard SOHO, ultraviolet sensors on GOES, and ground-based telescopes that caught faint glints during twilight, confirmed the same thing. The emission was real, not a camera artifact, not a software glitch. Something in the comet's vapor was releasing an electric, impossible blue. The scientific possibilities poured in quickly. One team proposed that the colour came from fluorescence, the way certain molecules absorb ultraviolet light and re-emit it at visible wavelengths. Carbon dioxide and cyanide, when bombarded by sunlight, can glow faintly blue. Another team suggested Rayleigh scattering, the same phenomenon that makes Earth's sky blue, as tiny dust grains scatter short wavelengths more effectively than long ones. Others pointed to plasma excitation, electrons from the solar wind colliding with the gas cloud, shaking atoms into glowing like neon signs. Any of these effects, or all of them together, could have painted the light we saw. But even after all the explanations were written down, something didn't quite fit. The intensity was too strong, the timing too precise. The flare occurred almost exactly at solar conjunction, when Earth couldn't see the comet directly. Only the instruments orbiting the Sun itself had the right vantage. It was as if the event had been timed for the one moment when human eyes were turned away. When the data reached Earth hours later, the astronomy community stirred with quiet excitement and disbelief. "We've never seen anything like this," one researcher said on a live stream. Another joked that Atlas had chosen the one night we couldn't look to make its grand debut. The humour couldn't hide the tension. Here was an interstellar visitor doing something profoundly unusual under circumstances that bordered on uncanny. The brightness didn't fade immediately. For nearly 2 days, the comet remained brilliant, enveloped in its electric blue cocoon. Then, gradually, it softened. The flare subsided, leaving behind a fainter but still glowing object, its colour drifting back toward a colder white. Some reports hinted at fragmenting features in the images, small knots of light breaking off from the core, but the glare near the sun made it impossible to be sure. It would take weeks for the geometry of orbits to shift enough for telescopes on Earth to see it again. During those days, the sun itself was restless. An X-class solar flare erupted on October 28th, the strongest in more than 2 decades. The blast sent auroras dancing across the skies of both hemispheres. Some wondered whether the timing was purely coincidence or whether the sun and the comet had interacted through some deeper, electromagnetic resonance. Could the enormous plasma sheath surrounding Atlas have tapped into the solar wind, creating a feedback loop that briefly intensified its glow? Models suggested it was possible, but unlikely. Still, the alignment of events, flare, brightness explosion, and blue emission, felt like a conversation between 2 celestial bodies. In the weeks that followed, astronomers pored over every frame. When they translated the raw data into graphs, they found hints of rhythmic pulsing in the brightness curve, repeating intervals that seemed almost musical. The pattern was too subtle to claim as evidence of anything deliberate, but it added another small thread to the tapestry of anomalies that Atlas had been weaving since its discovery. For those who prefer the language of metaphor to the precision of equations, what happened that day could be imagined as this. A traveller, silent for billions of years, passed close to a star, and for one brief instant it sang. Its song was blue light, brighter and purer than anything around it, and then it faded again into the dark. Scientists, of course, work to explain it, and they will, eventually. Data, when treated with patience, always yields to understanding. But for the public watching the composite videos released by NASA and ESA, the tiny bright speck blossoming and dimming against the halo of the sun, the moment carried a kind of quiet awe. Even if every photon could be accounted for, something in that sight reminded us why we watch the sky in the first place. Because sometimes, even cold matter can act like it remembers being light. As the blue faded, the question remained: what had changed inside Atlas? Was the outburst merely a surface event? Or had it reshaped the object entirely? A comet's core is fragile. Such a violent release could crack it apart, sending fragments spinning into new orbits. By early November, the first hints of this would begin to appear, setting the stage for yet another surprise. But for now, as the last traces of blue scattered into sunlight, the world had witnessed something it could barely name. A colour so pure it felt almost alive, and perhaps, somewhere in the quiet hum of instruments recording those fading photons, the universe was smiling, knowing that curiosity itself is the brightest light we have. When the first complete brightness data came in from the solar observatories, the numbers looked wrong at a glance. The curve that described how the light of 3i Atlas increased near the Sun was far steeper than any known law of cometary reflection. Normally, as a comet approaches the Sun, its brightness follows a simple rule: double the closeness, roughly quadruple the light. For Atlas, the brightness didn't just double or quadruple, it grew almost sevenfold faster than physics predicted. Astronomers wrote this down as a slope of about -7.5. But in plain words, it meant the object flared like a lantern doused suddenly with fuel, a rise so rapid that even seasoned observers paused to check their instruments twice. The blue colour, too, became a riddle of its own. Data from the SOHO cameras showed that the light was concentrated at the shorter wavelengths of the visible spectrum, pure azure, almost turquoise, yet it carried none of the green signature typical of cyanide gas, nor the faint pink of sodium ions. It was as though the comet had chosen a single note from the solar symphony and played it louder than the rest. To describe it scientifically, they called it spectral narrowing. To describe it emotionally, one might say it was a kind of visual purity, as if the colour of a clear mountain lake had taken form and hung in space. The halo of gas and dust surrounding the nucleus grew immense. The luminous envelope stretched roughly 300,000 kilometers across, about 25 times the diameter of Earth. That scale is difficult to picture. If Earth were at its center, the Moon would still orbit well within the glowing cloud. And yet, all of that brightness came from an object likely no more than a kilometer wide, smaller than a city. It was a reminder of how space loves contrast. Tiny cores producing vast, delicate atmospheres, silence giving birth to radiance. Teams at the European Southern Observatory and NASA's Goddard Space Flight Center began analysing the spectra. Some parts of the light looked like ordinary sunlight reflected off dust grains. Other portions were pure emission, light created by atoms and molecules themselves. Carbon dioxide and cyanide fluorescence accounted for much of it. When ultraviolet light from the sun strikes these molecules, they absorb the energy and then re-emit it as visible blue. But Atlas's emission was too intense for the usual models. It glowed brighter than any concentration of those molecules should have allowed. That meant something else was happening. Perhaps a new mechanism. Perhaps a combination of several. One intriguing idea involved very fine dust, smaller than a wavelength of light. When sunlight hits such grains, it scatters in a way that favours blue, just as Earth's sky does. This is called Rayleigh scattering, and though the mathematics behind it can fill a page, the feeling of it is simple. Tiny particles make big light. Another proposal pointed to plasma physics. The solar wind, a river of charged particles, may have struck the comet's gas cloud at just the right angle to create an electrical resonance. In that case, the blue wasn't a colour of molecules at all. It was the colour of electricity singing in thin air. As scientists compared notes, one subtle pattern stood out. The outburst wasn't gradual as in most comets. It had started almost instantaneously within a span of minutes and then decayed slowly over the next day. That timing looked like a mechanical trigger, like something had released pressure all at once. The idea of internal caverns of gas collapsing, or of sudden cracking under sunlight, gained traction, but even so, the light was too coherent, too symmetrical. The flare didn't come from one jet or one side of the comet. It came evenly, as if the whole body had exhaled together. The beauty of science is that it invites both skepticism and imagination to share the same table. For every scientist building new physical models, another asked quieter questions. What if Atlas's structure was layered in ways we hadn't considered? What if sunlight penetrated its crust and heated pockets from the inside out, setting off a chain reaction? Or perhaps, if one allowed a breath of poetry, it was responding to the sun in some resonant way, as a tuning fork responds to a note it recognizes. After the event, as the comet receded slightly from the sun, the blue emission began to soften. Observers described it turning from cobalt to icy silver, as if the object were cooling from its own fire. Instruments detected faint fragments drifting away, small glints moving independently through the haze. None seemed massive. Most were likely clumps of dust. But some showed steady, controlled motion, neither accelerating outward nor falling back. It was too early to know whether these were mere optical effects or the first signs of the nucleus breaking apart. For 2 days, Atlas held the attention of nearly every major observatory on Earth. Even radio telescopes tuned their antennas to listen, hoping to catch any signal that might accompany the visual outburst. They heard only the quiet hiss of the solar wind. Yet somewhere in that stillness, human imagination began to weave stories. Was this simply the most active comet ever seen? Or was it something else? Something built to wake under sunlight? Meanwhile, the sun itself seemed to join the spectacle. The X-class flare that erupted on October 28th reached its peak only hours before Atlas's brightness spike. Auroras danced across Earth's skies, painting them green and red. The coincidence was irresistible. Scientists know that solar activity follows its own cycles, but the timing raised questions about whether the two events could have influenced each other. The idea of electromagnetic coupling, a brief handshake between the sun's field and the comet's expanding plasma cloud, entered discussion. In gentle terms, it was like two instruments playing notes that happened to harmonize, each amplifying the other for a heartbeat of cosmic time. In the end, no single theory could explain every observation. Fluorescence, scattering, plasma excitation, structural collapse, all might have contributed, overlapping like instruments in an orchestra. What remained beyond doubt was that Atlas had broken records. Never before had a comet brightened so steeply, shone so blue, or expanded so quickly near the sun. It was not merely active, it was exuberant. And through all of this, Earth itself could not see it directly. From our vantage, the sun blocked the view completely. Only spacecraft circling elsewhere caught the spectacle. There was something poetic in that invisibility. For a brief moment, a cosmic performance unfolded just beyond our sight, radiant, mathematical and fleeting. When the Earth turned back toward the scene, the flare was already fading, its blue light dissolving into the golden haze of ordinary sunlight. Perhaps that is how most wonders pass through the universe, unseen by the ones who might have loved them most. But their traces linger, in graphs, in data, in the shared memory of those who stayed up through the night to watch their screens flicker with the light of something no one had ever witnessed before. And when the final report was filed, it carried a simple line that might have belonged equally to a scientist or a poet. The object displayed an exceptional increase in brightness, accompanied by an intense blue emission of undetermined origin. A sentence as calm as science requires, holding within it the quiet awe of everyone who saw a fragment of the impossible turn, just briefly, into light. In the same week that 3i Atlas shone its electric blue light near the sun, our own star began to tremble with energy, The surface of the Sun is never still. It's a restless sea of plasma where waves of magnetism rise and fall like tides. But in late October of 2025, that restlessness turned to fury. On October 28th, just a day before the comet's great flare, an enormous X-class solar storm erupted. It was the most powerful in more than 20 years. The blast sent a surge of charged particles racing outward through the solar system, and when those particles reached Earth, they painted the sky with auroras visible as far south as Italy and Texas. Curtains of green and red light rippled across the atmosphere like cosmic silk. For many who saw them, it was a beautiful coincidence, an earthly echo of the comet's sudden brightness, a duet of light between the planet and the sun. But for astronomers studying Atlas, the timing raised questions too perfect to ignore. Could the solar flare and the comet's explosion of blue light be connected? Or was it simply coincidence? Two brilliant flares overlapping in the same celestial week. To understand why this idea captured imaginations, you have to picture how deeply intertwined the Sun and its surroundings really are. The Sun breathes a continuous wind of charged particles, a stream of electrons and protons that flow outward in all directions. This wind fills the solar system, creating an invisible bubble called the heliosphere. When an object like a comet moves through this environment, its gas and dust interact with that wind, forming tails that always point away from the Sun. Most of the time, the wind is gentle, steady, predictable, almost polite. But when a solar flare erupts, the flow becomes a storm, dense and electric, capable of shocking whatever lies in its path. At the moment of Atlas's perihelion, the Sun's magnetic field lines were twisted and vibrating, releasing an enormous burst of energy. If the comet's vaporous halo was large enough, and by then it had grown to a diameter hundreds of thousands of kilometers wide, it might have acted like an antenna, catching the solar wind and glowing brighter as those energetic particles raced through it. Some physicists suggested that the comet's plasma sheath could even have reflected or refracted part of that energy, creating brief bursts of light that looked like pulses. To anyone studying the data from afar, it might appear as if the comet had its own internal rhythm, a flicker matching the heartbeat of the Sun. But there was another layer of intrigue. The location of Atlas at that time was almost directly behind the Sun from Earth's perspective, a position astronomers call solar conjunction. That meant we couldn't see it with ground-based telescopes at all. Our line of sight was blocked by the Sun's glare. Only satellites positioned off to the side could observe it directly. So when the blue outburst happened, the event unfolded unseen by human eyes. It was as if the visitor had chosen to perform its greatest act in private, hidden behind the stage lights. When the data finally streamed back, scientists began to piece together a timeline. The solar flare peaked at midday on the 28th. The brightness spike from the comet began only hours later. The chance of that overlap being random was small, but not impossible. After all, the Sun produces countless flares each year. Still, the coincidence was irresistible. Some researchers used the word resonance. Others preferred sympathetic response, a poetic way of saying that maybe the two phenomena were linked through invisible fields. In the language of plasma physics, this idea is called coupling, the way two charged systems can exchange energy if their frequencies align. Imagine two tuning forks vibrating at slightly different pitches. If you strike one, the other may begin to hum as well, its motion amplified by the resonance. In this analogy, the Sun is one tuning fork, its magnetic waves rippling outward, and the comet's vast plasma cloud is the other, catching those vibrations and re-emitting them as light. Of course, the reality is far more complex. The mathematics of magnetohydrodynamics, the study of charged fluids like plasma, is among the most intricate in science. But to grasp the spirit of it, you only need to imagine two instruments briefly sharing a note across space. Some observers even noticed that the shape of the comet's halo changed after the flare. In the hours that followed, Its tail curved sharply, as if pushed by a sudden gust. The geometry suggested a direct hit by the solar wind. If so, Atlas might have responded exactly as physics would predict, an expanding cloud reacting to a blast of charged particles. The beauty of that explanation lay in its simplicity, nature in perfect synchrony, producing a spectacle that looked almost intentional. Yet others wondered if something more was happening inside the comet itself. Could the intense radiation have triggered internal fractures, exposing fresh ice and releasing stored gas in a burst of pressure? In that case, the solar flare didn't cause the blue emission directly. It merely awakened what was already waiting within. That idea made Atlas seem less like a passive victim of solar weather, and more like a participant in a cosmic dance, responding to its partner's energy with its own luminous gesture. Across online forums and observatory networks, the event became a topic of quiet debate. Some researchers argued for coincidence, others for connection. A few simply marvelled at the timing, but all agreed on one point. Whatever had happened, it was unique. No other interstellar visitor had behaved quite this way. As the flare's effects subsided and the sun returned to calm, Atlas began its slow emergence from behind the solar glare. Telescopes waiting on Earth finally caught its light again in early November. It was dimmer now, but still tinged with that same faint cold blue. The giant envelope that had surrounded it during the flare was thinning, drifting outward like fog at dawn. The main body appeared intact, though a few hints in the images suggested possible fragmentation, small pieces separating from the core. When the first processed images arrived at research centres, scientists found themselves staring at something both fragile and profound, the afterglow of an encounter between a wandering object from another star and the restless heart of our own. It was a meeting written in light, a flash that had lasted less than a day, yet carried the stories of billions of years. For those who study the heavens, such moments are humbling. They remind us that the sun, our familiar source of warmth, is part of a wider network of energies stretching across the cosmos. The same forces that shape auroras above our poles can reach out to touch a fragment of ancient ice from another system, millions of kilometers away, and make it sing in colour. Whether the relationship between Atlas and the solar storm was cause or coincidence may never be settled completely, but it hardly matters. The universe has a way of aligning its rhythms, whether by chance or by law, in ways that feel almost human. And as the blue light faded and the sun's roaring quieted, what remained was the simple truth that we had witnessed a rare conversation, one star speaking in flares, one traveller answering in light. And now, with the flare behind it, and Earth turning back toward its path, Three-Eye Atlas continued its journey, cooling, dimming and preparing perhaps for yet another surprise as it drew nearer to our planet. The story was far from over. It had only changed the key, softening from the brilliance of fire to the quiet pulse of mystery once again. When a comet glows, we usually think of what we can see, a soft tail, a shimmer of light. But some discoveries begin not with sight but with sound. Not the kind you hear with ears, but with antennas stretched wide across the Earth, listening to the quiet hum of the universe. That's how the story of the radio murmur of Three-Eye Atlas began, not as a flash of light in the sky, but as a pattern of whispers in the hydrogen line, the frequency where the cosmos itself seems to breathe. The hydrogen line is a single, steady note played by the universe's most common element. It hums at about 1.42 gigahertz, a gentle radio tone produced when the electron inside a hydrogen atom flips its orientation. Every astronomer and every radio telescope knows this sound. It is the background heartbeat of our galaxy. SETI, the search for extraterrestrial intelligence, has listened to that frequency for decades because hydrogen is everywhere, and any civilization wishing to speak across the stars might choose the same universal language. So when the giant meter-wave radio telescope in India, GMRT, picked up faint rhythmic pulses coming from the direction of 3I Atlas on October 30th, ears perked up. The signal wasn't continuous. It came in brief intervals, almost like breath. Each burst lasted a fraction of a second, separated by gaps that seemed oddly structured. 8 units apart, then 13, then 8 again, then 5, then 13, then 8. To a mathematician, that rhythm felt familiar. It mirrored the Fibonacci sequence, the pattern that appears everywhere in nature, in the spirals of shells, in the petals of sunflowers, in the spacing of galaxies. At first, everyone assumed it was coincidence, or interference from earthly sources. Radio telescopes are exquisitely sensitive. They can pick up a microwave oven opening on the other side of a campus. But when other observatories, the Parkes Observatory in Australia and the Allen Telescope Array in California, pointed their dishes in the same direction, they too noticed faint repetitions at the same frequency. The reports were cautious. The data wasn't identical, the timing not perfect, but something seemed to be there. A faint heartbeat at the wavelength of hydrogen, the quietest and most universal tone we know. SETI released a statement almost immediately, gentle but firm. No confirmed artificial signal has been detected from 3I Atlas. Further verification is ongoing. NASA echoed the same words. For professionals, it was a familiar dance between curiosity and restraint. They'd been here before. In 1977, the WOW signal, a sudden strong radio pulse from the constellation Sagittarius, had sparked similar excitement. It too came near the hydrogen line. It too never repeated. For nearly 50 years, people have wondered if that long-ago whisper was a message, or merely nature playing chords that sounded familiar to us. And now, from almost the same direction in the sky, the instruments were listening again. The resemblance was uncanny enough to feel poetic. Sagittarius, the direction of the galaxy's centre, the place from which Atlas itself seemed to have come. A faint whisper, a repeating pattern, a question echoing through the same part of space across half a century. Coincidence, perhaps, but the kind of coincidence that makes human hearts lean forward. Scientists, though, are trained listeners. They know how easily we can mistake pattern for intention. Our brains are tuned to recognize rhythm. We find faces in clouds and music in static. To guard against that bias, the teams ran careful tests. They checked whether the signal vanished when the telescope moved slightly off target. It did. They reversed the receivers, changed frequencies, compared with control data from blank patches of sky. Some of the pulses faded under these tests, others stayed faintly present. The verdict was uncertain, which, in science, means the story isn't finished. Still, the numbers had a haunting symmetry. The interval between pulses was not random noise. It formed ratios close to Fibonacci proportions, 8 to 13, 13 to 21, and back again. Nature does this often. Spirals, storms, and even galaxies follow the same mathematics because it's efficient. It minimizes energy and space. Perhaps the comet's gas jets were venting in rhythmic bursts, driven by its rotation. Perhaps the interaction of sunlight and plasma created oscillations that happened to mimic those familiar ratios. It would be a beautiful accident, and no less meaningful for being natural. For radio astronomers, the real wonder wasn't whether the signal was artificial or not. It was that they could detect such faint whispers from a traveller less than a kilometre wide, tens of millions of kilometres away. The sensitivity of modern instruments is extraordinary. They can hear a phone call's worth of power across the gulf between planets. To translate that into everyday language, if someone were to light a single candle on the moon, the best telescopes could sense its heat. That is how delicately we're now able to listen. Meanwhile, social media and news headlines began to hum with excitement. Alien probe? Cosmic beacon? The public imagination caught fire far faster than any scientific review could keep up. Harvard's Avi Loeb, never one to shy from bold hypotheses, suggested that the anomalies surrounding Atlas, its metallic content, its precise geometry, its Fibonacci-like signals, deserved open consideration. NASA responded quietly but firmly. All data was being shared with the International Astronomical Union, and nothing yet pointed to anything beyond natural explanation. Inside observatories, the tone was different, less sensational, more reverent. Researchers played back the recordings, a faint rising hiss punctuated by brief beats. To the human ear, it sounded like rain tapping against a window or a heartbeat heard through water. Some joked that the galaxy was singing scales. Others, more thoughtful, sat in silence, feeling the weight of being alive at a time when even a comet's static could make us question our place in the cosmos. If the pulses were real, they could come from many things: plasma oscillations in the comet's tail, resonance in its magnetic field, even reflections of the solar wind bouncing off its ionized gases. But the romance of it, a repeating rhythm at the hydrogen frequency, was irresistible. The hydrogen line has always been our symbolic channel to the stars, the place we've promised to listen and to speak, if ever there was someone out there listening too. And so, as October gave way to November, 3 Atlas carried not just the light of its blue flare, but the echo of these faint radio murmurs. The data kept coming, messy, ambiguous, fascinating. Most likely the pulses would turn out to be natural, but as one astronomer wrote in her notes that week, even a natural whisper from an interstellar traveller is worth staying up for. In the quiet hours before dawn, as telescopes turned back toward the cold sky, you could almost imagine the scene. A dozen radio dishes tilted toward the same dark region, their metal faces glowing faintly under moonlight, all listening together for something older than words. Whether or not Atlas was speaking, the act of listening itself was the message. Proof that on one small planet, curiosity still keeps watch while the rest of the world sleeps. When the bright blue light of Atlas finally faded, scientists expected the object to settle into calm again, a small, cooling comet continuing its flight. Instead, a new mystery appeared, one even stranger than the glow itself. In the final hours of October, as the solar storm waned and telescopes adjusted their instruments for another round of observation, data from 2 spacecraft, ESA's JUICE mission and NASA's Parker solar probe, hinted that the comet had changed shape. What had been a single point of light now seemed to shimmer, breaking into several distinct sparks. At first, analysts thought it might be a sensor glitch or cosmic rays hitting the cameras. Spacecraft operating near the Sun often collects noisy data. But as the images accumulated, the pattern grew consistent. The main body of 3I Atlas had split, not into random debris, but into 7 luminous fragments moving in gentle formation. 7 small lights, each gliding along slightly different paths, like pearls sliding on invisible strings. Fragmentation isn't unusual for comets. Many fall apart when they approach the Sun. Heat fractures the surface, gases trapped inside expand, and the nucleus shatters like ice under pressure. But the behaviour of Atlas's fragments didn't fit that script. When scientists traced their motion, 3 of the pieces showed something that shouldn't have been possible: deceleration. In the vacuum of space, where there's almost no friction, an object can't slow down on its own unless some external force acts upon it. These fragments weren't drifting away like shrapnel. They were adjusting, as though steering gently against the current of sunlight. To describe it simply, imagine blowing soap bubbles into a breeze. Most will scatter wildly, but a few might seem to pause mid-air, swirling in place before moving on. That's what the sensors saw, 3 fragments behaving as if aware of balance. The scientific reports used more measured words, non-ballistic motion, but the phrase, in human language, meant that these pieces weren't just falling where physics would send them. Something, perhaps internal outgassing jets, perhaps an asymmetric structure, was nudging them, softly and steadily. As the images continued, the 7 fragments formed a faint pattern, not a perfect line, not random chaos, but a loose spiral, each piece trailing slightly behind the other, turning slowly around an unseen centre. The resemblance to a Fibonacci spiral, the same mathematical curve whispered earlier in Atlas's radio rhythms, did not go unnoticed. It could be coincidence, of course. Nature loves spirals, hurricanes, galaxies, seashells, all built by the same principle of growth. Yet to see that same geometry repeated in fragments of a disintegrating interstellar visitor was, at the very least, poetic. NASA's Planetary-Defense Coordination Office received the reports immediately. Even though the fragments were far smaller than the original nucleus, any breakup event near Earth's orbit triggers an automatic review. But the numbers offered reassurance. The predicted trajectories showed the cluster would pass at a comfortable distance, around 0.06 astronomical units, roughly 9 to 10 million kilometers. For comparison, that's 25 times the distance from Earth to the Moon. Safe, but still close enough to study with radar and optical telescopes in December, when the fragments would swing by together. Meanwhile, curiosity outweighed caution. Teams across the world began to model what could cause such controlled separation. The first idea was symmetric venting. Jets of gas emerging from opposite sides, gently pushing the comet apart like air from a pair of lungs. Another suggestion was that Atlas's core might have contained cavities filled with frozen carbon dioxide. When heated unevenly, each pocket could burst in turn, releasing just enough force to guide a fragment's drift. The pattern, then, would be nature's choreography, not design. Yet the more the data was studied, the more symmetrical it appeared. For the Parker Solar Probe, the readings were even more curious. Passing through the outer edges of Atlas's expanding gas cloud, its instruments detected fluctuations in magnetic fields, small oscillations that repeated at regular intervals. These ripples weren't strong enough to qualify as radio signals, but they seemed synchronized with the moment each fragment separated. It was as if the comet exhaled in pulses, each breath marking the release of a piece of itself. Scientists hesitated to use words like intentional, because in science, intention belongs to minds, not matter. But the description, coordinated release, appeared in more than one report. For the first time, discussions of Atlas carried a tone of something close to reverence. If it was natural, it was the most graceful destruction ever recorded, a breakup conducted with mathematical elegance. From Earth, the fragments were invisible for now, hidden in sunlight. But astronomers could simulate what the cluster might look like when it re-emerged. 7 specks tracing faint blue arcs across the sky, each leaving behind a wisp of gas. The mental picture stirred something in people, the same quiet emotion that comes from watching migrating birds, each wing beat separate but part of one large emotion. Among those following the event, 2 moods grew side by side. One was calm professionalism, checking orbits, refining calculations, running models. The other was wonder, the kind that doesn't fit neatly into equations. Journalists began calling it the celestial murmuration, borrowing the word used for the coordinated flight of starlings. On social media, animated diagrams showed the 7 fragments looping together like dancers on a dark stage. The idea of design floated again, half serious, half metaphor. Even within the data itself, there was a quiet beauty. When plotted on a 3-dimensional map, the fragments formed a curve that opened outward in a slow spiral. The ratio of distances between them, 1 to 1, 1 to 2, 2 to 3, and so on, matched the same pattern that underlay the earlier radio bursts. Some scientists rolled their eyes at the comparison. Others admitted it was difficult not to notice. But everyone agreed on one fact. 3I Atlas had transformed. What began as a single blue wanderer was now a small constellation of lights, each carrying a fraction of the original's mystery. By the start of November, the new cluster had stabilized. the fragments continued on their outbound path, following trajectories that would bring them near Earth's orbit in mid-December. As predictions converged, the date of December 19th, 2025 emerged as the moment of closest approach. That would be the best opportunity to observe the fragments individually, to test whether they were mere ice and dust or something sturdier. For now, though, the story remains suspended between explanation and imagination. Perhaps these 7 lights were just pieces of a dying comet, drifting apart in a beautiful accident of symmetry. Or perhaps they were something rarer, evidence of a process we had never seen before, a kind of cosmic self-organization written in numbers and light. Whatever the truth, the image lingered, a single visitor that came from the darkness and, in its passing, divided itself into 7 quiet sparks, moving not chaotically but gracefully, as though even in disintegration it wished to leave behind a pattern worth remembering. When a comet fragments near the inner solar system, alarms do not ring, but attention sharpens. In late October of 2025, just after news of 3I Atlas's breakup reached Earth, the phone lines and data channels between space agencies began to hum quietly. At NASA's Jet Propulsion Laboratory in California, teams at the Planetary-Defense Coordination Office convened with their counterparts at the European Space Agency, joined by specialists from Japan, India and the International Asteroid Warning Network, known simply as AWN. It was an emergency coordination call, but the mood was not fear. It was focus and perhaps a touch of awe. The first step was confirmation. 7 fragments had indeed separated, none larger than a few hundred meters across, each following the same general path as the parent object. Calculations showed that all would pass Earth safely on December 19th, at a distance of roughly 9 million kilometers, about 25 times farther than the Moon. No impact risk became the phrase, repeated in every briefing. But no risk in planetary defense language does not mean ignore. It means observe everything, just in case nature decides to rewrite the script. Dozens of observatories around the world joined the effort. Radar arrays in Goldstone and Canberra prepared to bounce signals off the approaching fragments once they came into range. Optical telescopes in Chile, Spain and Hawaii scheduled nights of observation, while radio instruments from California to Italy cleared frequencies to listen for any continuing emissions around the hydrogen line. In total, 37 observatories formed a temporary global orchestra, each tuning to a slightly different note. Together they would monitor the visitor around the clock for the next several months. The coordination looked almost poetic when visualized on a map. Dots of light scattered across continents, all aimed toward the same region of sky. One astronomer described it as a chorus of telescopes keeping night watch, not out of fear but curiosity. And that was true. There was no panic, only a kind of quiet respect, an acknowledgement that the universe had presented something rare and that humanity was mature enough to treat it with calm wonder. NASA's public affairs team faced a more difficult task, communicating that calm to the world. After the blue flare, the radio murmurs, and now the 7 fragments, speculation had already escaped into the internet like a breeze through an open door. Videos titled Alien Probe, confirmed appeared within hours, comment sections filled with claims that governments were hiding the truth. Some quoted Avi Loeb, the Harvard astronomer who had famously suggested that Oumuamua might have been artificial, and who now hinted that Atlas's behaviour deserved similar attention. NASA responded with its usual balance of patience and precision. All data remain under review, their statement read, and no confirmed signs of artificial origin have been found. They explained the process openly. Each observatory would release its own results, which would then be compared for consistency. Transparency, they hoped, would cool the flames of rumour. Still, a sense of mystery clung to every update, because even in ordinary science, No explanation yet sounds tantalizingly close to something extraordinary. Inside the scientific community, the tone was different. Researchers traded files, discussed calibration methods, and scheduled follow-up time on powerful instruments like the Very Large Telescope in Chile and the ALMA radio array in the Atacama Desert. No one shouted, "Discovery!" They were too busy checking numbers. Yet beneath the caution, there was excitement. How often does an interstellar traveller break apart right in our neighbourhood? How often do we get to study fragments from another star drifting slowly past our own? One of the most striking things about the coordination effort was its sense of unity. Political borders meant nothing to the people watching Atlas. Night after night, as data streamed in, scientists in one hemisphere handed off to colleagues in another, ensuring continuous coverage. When the fragments slipped behind daylight in Europe, telescopes in South America picked them up again. When the Pacific turned toward morning, Asia resumed the watch. It was as if Earth itself had become a single, rotating eye. For the public, the contrast between online noise and professional composure was instructive. Planetary defense is built on patience. It's about long time scales, careful confirmation, and the humility to admit when something is uncertain. A real hazard would generate clear warnings, numbers, probabilities, public briefings. What was happening with Atlas was different. It was science in its purest form, observing something unprecedented simply because it exists. The phrase planetary defense can sound dramatic, as though giant lasers are ready to fire into space. In reality, it's quieter, a network of eyes, equations, and communication channels linking hundreds of researchers who trust one another with the sky. Most of their work involves cataloguing harmless objects, refining orbits, updating maps of dust trails. Their weapon isn't aggression, it's understanding. And when a true mystery appears, they meet it not with fear, but with notebooks and coffee cups. In the days following the coordination call, data from Parker's solar probe confirmed that the fragments were releasing streams of gas consistent with gentle outgassing, not propulsion. The mild deceleration observed earlier was most likely caused by jets of carbon dioxide pushing back against sunlight. Nature, it seemed, had found another clever way to mimic intention. The fragments were not steering, they were breathing. That explanation didn't silence fascination, of course. Humans are storytellers. We can't help but imagine what we see in familiar terms. The 7 fragments became the 7 travellers, the 7 lanterns, the 7 seeds. Some journalists wrote essays about how, if the object were artificial, it might be a probe scattering sensors to sample the solar system. Others took the poetic route, suggesting that the visitor was offering a lesson in humility. Even when we think we've seen everything, the cosmos reminds us there are patterns we still don't understand. Within the observatories, humour softened the long nights. Someone posted a sign near the data server. If the aliens call, please log the frequency. Another left a note. Remember, extraordinary evidence requires extraordinary patience. That phrase, the patient version of a well-known quote, captured the mood perfectly. The scientists didn't deny the wonder, they simply refused to rush it. By early November, the International Astronomical Union released a collective statement confirming the global observation campaign. No hazard to Earth, it repeated, but high scientific value. The wording may have been bureaucratic, yet behind it lay a kind of human beauty. Cooperation without drama, discovery without panic. If you had looked up at the night sky then, you wouldn't have seen anything unusual. The comet was hidden in the sun's glare, its fragments too small and distant for naked eyes. But scattered across the world, from mountaintop domes to quiet desert stations, hundreds of people were awake, watching, listening, and recording. Together they were writing the next chapter of a story that began long before Earth existed. A story of objects wandering between stars, of minds curious enough to follow them, and of a planet that, for all its chaos, can still respond to wonder with calm. And perhaps that is the truest meaning of planetary defense, not protection through fear, but through understanding. A reminder that vigilance can be peaceful, that attention can be an act of gratitude. Under that shared watch, Atlas drifted onward, its 7 sparks fading slowly into the dark, leaving behind not danger, but connection, a quiet demonstration of how curiosity itself defends us best. Perhaps the simplest story we can tell about 3i Atlas is also the most elegant, that it is a natural comet, but one born in a place far colder and richer in exotic ices than anything in our own solar system. In this version, there is no hidden engine, no coded message, only chemistry doing what chemistry does best, responding to light in beautiful and unexpected ways. Comets are, in essence, time capsules. They hold the raw ingredients of the systems they came from, frozen since their creation. In our neighbourhood, most comets are made mainly of water ice, with traces of carbon dioxide, ammonia and organic dust. But imagine a system orbiting a cooler, fainter star, or one that formed at the dim outer edge of a protoplanetary disk. There, the heat from the star would never have reached far enough to boil away the lightest molecules. Carbon dioxide, methane, even carbon monoxide could freeze solid and stay that way for billions of years. If such an object were ever ejected from its birthplace and sent wandering through interstellar space, it would carry with it those delicate, volatile ices, sleeping beneath its surface, waiting for the touch of sunlight. When Atlas entered our solar system, it must have felt as though it were waking from an eon-long dream. Even 5 times farther from the sun than Earth, the faint warmth of sunlight began to reach its surface. But instead of melting water ice, it was the carbon dioxide that stirred first, escaping as gas through microscopic vents. That early exhalation created the coma we saw in May 2025. The haze that formed long before ordinary comets would have awakened. The reversed ratio of gases, with 8 parts carbon dioxide to 1 part water, suddenly made perfect sense. As the comet drifted inward, that steady breathing intensified. By the time it reached the orbit of Jupiter, its jets were already strong enough to shape its own tail. The faint anti-tail that pointed toward the sun may have been nothing more mysterious than sunlight pushing against these carbon-rich particles, a delicate interaction of gravity and wind. Seen through telescopes, it looked uncanny, but in this story it was just nature's geometry, the same play of forces that paints every comet's path. Even the deep cobalt hue that stunned astronomers at perihelion can find a natural explanation. When ultraviolet light strikes carbon-bearing molecules such as carbon monoxide or cyanide, they fluoresce. They absorb invisible light and re-emit it in visible blue. It is the same process that makes some minerals glow under black light, or ice glint blue in a glacier. At the intense energy levels near the sun, those emissions can become dazzlingly bright. The brightness law that rose 7 times faster than expected might not have required exotic physics at all, only an abundance of these molecules, each acting like a miniature mirror for ultraviolet sunlight. The object's fragmentation could also fit neatly within this tail. Many comets crumble near their closest approach to the sun. They are fragile, porous mixtures of ice and dust. When one side heats more rapidly than the other, cracks form. Gas escapes, creating jets that push pieces apart in slow motion. The 7 fragments of Atlas might simply be the petals of a cosmic flower, unfolding under solar heat. Their graceful, almost mathematical spacing may reflect the rhythm of rotation combined with the physics of pressure release. What looked deliberate could have been merely the universe expressing symmetry, something it does often and without thought. The nickel seen in its spectrum, absent the usual partner of iron, might trace back to the environment where it formed. In certain cold regions of space, heavy metals condense in layers, separating like oil and water. Over time, the lighter iron could have oxidized and drifted away, leaving purer nickel grains frozen into the surface. When the sun's heat finally freed them, they vaporized into that strange spectral glow we interpreted as refinement. Even the unusual polarization of its reflected light, those backwards tilted waves, can arise naturally from very smooth dust grains coated with these metallic compounds. To a telescope, it might look engineered. To nature, it's just physics written in shining dust. For scientists who lean toward this interpretation, Atlas is less a puzzle and more a gift, an untouched sample of another world. It is evidence that planetary systems everywhere build comets not unlike our own, but with variations that record their stellar climates. Just as a tree's rings hold a history of the seasons, the layers of ice within Atlas may hold a record of temperatures, radiation levels, and chemistry from a star that died long before ours was born. This story of a super volatile comet also carries a kind of quiet poetry. It suggests that the universe still has places so cold that gases we think of as vapor can exist as solid stone. It reminds us that even silence has variety, that beyond the reach of our sun, frozen worlds drift in the dark, keeping their delicate compositions intact until chance brings them near enough for a brief, radiant sigh. When skeptics argue that Atlas's behaviour seems too structured, defenders of this natural model smile gently. Nature, after all, has a long history of creating patterns we once thought impossible. The rings of Saturn, the hexagons on its poles, the spiral arms of galaxies, all look like art until mathematics explains them. To see purpose in a comet's rhythm may simply mean that our minds recognise the same elegance that matter does when it follows its laws. If this version proves true, then the message of Atlas is a simple one, that the cosmos is capable of beauty without intent, and that perfection does not require design. Its early awakening, its blue glow, its fragmentation into 7 pieces, all could be the natural choreography of physics playing itself out across time. And that, in a way, is even more wondrous, because it means that the universe does not need mystery to be miraculous. It already is. So perhaps the story ends there, a frozen traveller from another system, breathing carbon dioxide instead of water, catching fire briefly in our sun's embrace, then scattering its dust and moving on. In the cold vacuum it will fade again, its gas is spent, its fragments cooling as they drift toward the stars. Long after the instruments fall silent and the headlines fade, the truth of it will remain suspended between curiosity and calm. If you could follow one of those fragments out into the dark, you might find it spinning slowly, its surface glimmering with frost. No signal, no secret, just light reflecting from metal grains, whispering the quiet truth that nature, left to itself, can create stories far stranger than any we could invent. There's another story that scientists tell, one that leans less on ice and more on energy. A tale where sunlight and magnetism become the artists, painting colours across space. In this version, the strange blue glow of 3i Atlas wasn't born solely from chemistry. It was born from a dance of charged particles, the same kind of invisible electricity that makes auroras ripple above the poles of Earth. When the sun breathes, it doesn't just give off light. It sends out a constant stream of plasma, a wind made of electrons and protons moving at hundreds of kilometers per second. This solar wind stretches across the solar system, carrying with it the sun's magnetic field. Whenever this stream collides with another magnetic field, a planet's or even a comet's, the two can interact in ways that release bursts of light. Scientists call this magneto-hydrodynamic coupling, though you can imagine it more simply as a cosmic handshake of electricity. For most comets, this handshake is faint. Their plasma tails shimmer lightly, a sign of the sun's breath brushing past. But 3i Atlas arrived during one of the sun's most tempestuous moods. The massive flare of October 28th, an X-class eruption, the highest class on the solar scale, had just surged outward when Atlas reached perihelion. The timing was uncanny. The flare sent a wave of charged particles and magnetic disturbances racing through space, and the comet, wrapped in its vast envelope of gas, may have caught that wave like a sail catching wind. To visualize this, think of a musician playing a glass harmonica. A circle of glass bowls spinning slowly while wet fingers touch their rims, making them sing. The sun's charged particles would have been those fingers, brushing against the layers of plasma surrounding Atlas. Each touch could make the gas ring with energy, releasing light at the blue end of the spectrum, the colour of high excitation, the hue of electrons jumping between levels before falling again. If that resonance happened across the entire coma, the effect would have been global. Not a small jet of gas, but the whole cloud singing in response. The steep rise in brightness that puzzled scientists, the one they described mathematically as a slope of -7.5, meaning a sevenfold increase beyond what the distance should allow, could have been the visible result of this magnetic performance. For a moment, Atlas might have become a living amplifier for the sun's storm. When the flare's particles reached Earth a day later, auroras blazed across half the planet. To people watching from the ground, the sky looked alive, curtains of colour rippling as if answering the same invisible music. On Earth, those lights were shaped by our magnetic field. Around Atlas, the same physics could have played out on a smaller, more delicate scale. Electrons spiralling along magnetic lines, lighting the gas with the same ethereal tone, only bluer. This theory, though romantic, is grounded in plasma science. Researchers studying the Parker Solar Probe's data found that the local magnetic field near Atlas had oscillated rapidly during the flare. Small tremors of energy moving in pulses. Each pulse matched a faint shift in brightness, recorded by cameras on SOHO and Stereo A. It was as if the comet's glow followed the rhythm of the sun's heartbeat. Whether that rhythm came from direct electrical connection or from shock waves moving through the solar wind, no one could yet say. There are other clues that point toward an electromagnetic origin. The radio murmurs detected later around 1.4 GHz, the hydrogen line, could have been the echo of those same interactions, the sound of plasma waves converting into radio frequencies. Space is full of such conversions. Planets with magnetic fields often sing this way. Jupiter in particular produces haunting radio tones when its magnetic field tangles with that of its moons. If Atlas was large enough and its coma wide enough, it could have generated similar resonant tones as the solar wind swept through it. Skeptics of this model point to the energy requirement. For a comet to glow as brightly as Atlas did, the incoming charged particles would have had to deposit enormous amounts of power into its gases, far more than typical solar winds can carry. But the defenders of the theory remind us that the sun's flares are not typical. The October flare was one of the strongest of the cycle, its energy millions of times greater than all the electrical power humans use in a year. Even if a small fraction of that energy touched Atlas, it could easily have caused the outburst. To explain the symmetry of the glow, how it expanded evenly in all directions, scientists proposed that the comet's coma acted as a conductor. When the wavefront of the flare reached it, the ionized gas around the comet might have redistributed the energy instantly, creating a luminous bubble rather than a lopsided jet. In essence, the comet became a floating plasma sphere, briefly illuminated from within. The light would fade naturally as the electrons cooled, just as auroras fade when night ends. There's something quietly humbling about this explanation. It doesn't require the comet to be alive or designed. It simply lets it be what it is, a piece of the universe responding to its parent star, the way dust motes dance in a beam of light. The beauty of the event lies in timing, in the delicate coincidence of a flare's path and a comet's orbit crossing at exactly the right instant. For many scientists, that coincidence is enough. They see Atlas as proof that even without intelligence, nature can choreograph scenes that feel deliberate. The universe needs no artist to paint its light. It needs only time and chance. And yet, even among those who accept the plasma explanation, there's a touch of poetry in how they describe it. The sun's electric caress, one researcher called it in a late-night interview, a moment when the star brushed against something older than itself and made it sing. That image caught on. It appeared in articles and public talks, a phrase that bridged the gap between science and wonder. So perhaps this is how we should think of Atlas. Not as an intruder or a machine, but as a collaborator in a cosmic duet. The sun provided the music. The comet became the instrument. Together they played a song of light that lasted only a day, but travelled across millions of kilometres of space, reaching every telescope that was listening. When we look back on that blue glow years from now, the truth might turn out to be simple. An electromagnetic coincidence, perfectly natural. But even if that's all it was, it reminds us that beauty doesn't depend on meaning. Sometimes it's enough that light finds something to dance with, and that we are here to see it happen. There is, of course, a third story, a more daring one. It begins not with physics, but with a question that has followed humanity for as long as we've looked at the sky. What if we are not the only ones watching? What if Three-Eye Atlas, with all its symmetry, its spirals, and its strange measured rhythm, is not simply a fragment of ice and dust, but something built? Not a comet, but a kind of surveyor, an instrument designed to drift between stars, waking only when sunlight touches it again. To entertain such an idea, even for a moment, is to step delicately between science and imagination. It requires humility, not belief. Scientists who speak of this hypothesis always do so carefully, as if walking on snow that might collapse under their feet. They are not proclaiming that Atlas is artificial. They are asking whether, if such a thing were ever to exist, this is what it might look like. Imagine a probe designed for endurance rather than speed, a seed launched from a civilization so ancient that its makers may no longer exist. To cross the distances between stars, it could not depend on fuel or direction. It would need to travel like a comet, using only the forces of gravity and light. Most of its life would be spent in silence, drifting through the dark. But when it passed close to a star, that light could awaken it, powering whatever instruments it carried. The warmth would be both its sunrise and its signal to stir. In this scenario, the blue flare of October 29th takes on a new role. Instead of a natural outburst, it could have been the moment the surveyor awoke, a system reactivating after eons of sleep. The pattern of brightness, the evenness of the light, the harmonic intervals that seem to match natural ratios. They might not be coincidences, but diagnostics, checks of alignment, pulses for navigation, or even data encoded in the simplest possible way. Numbers that echo patterns found everywhere in nature, like the Fibonacci series. If we imagine that the surveyor were meant to map, not to speak, its behaviour makes quiet sense. The slow rotation, the release of 7 fragments, each moving in measured arcs. These could be sampling devices or autonomous modules, spreading out to record magnetic fields or solar flux from different angles. They wouldn't need propulsion as we understand it. Outgassing jets or shape changes could provide gentle steering, using sunlight itself as a rudder. To an observer, it would look like non-ballistic motion, pieces drifting but adjusting, as though aware of balance. The chemistry of Atlas fits this story in eerie ways. The presence of pure nickel without iron could imply material selection rather than chance. Nickel is excellent for resisting corrosion, a natural choice for a long-lived structure exposed to radiation. The reversed light polarization, suggesting smooth, glass-like dust grains, might not be random, but the sign of a surface polished by design, made to reflect efficiently or to control temperature. Even the comet's early awakening, its tendency to vent gas at great distance, could resemble a system designed to test its surroundings long before approaching a star too closely. Of course, Every one of these details can be explained by ordinary physics. The beauty of science is that it always offers simpler explanations before reaching for the extraordinary. And yet, the more we study the universe, the more we learn that extraordinary simplicity can also be the mark of intelligence. A message need not be complicated to be intentional. In fact, the simplest messages are the ones that survive across millennia. A pulse at the hydrogen line, a repeating mathematical ratio, these are ideas that any mind, anywhere, could recognize. The philosopher Carl Sagan once wrote that any truly ancient civilization would not shout across space with words, but whisper in the universal language of mathematics and light. If that is true, then Atlas's faint Fibonacci rhythm might be the kind of whisper we'd expect, not a greeting, not even communication, but evidence of pattern. A structure that records data powered by starlight, reporting not to us but to the universe itself. And yet, even this idea does not need to imply purpose. Suppose the surveyor is real, but not deliberate. Perhaps it's a relic, a derelict fragment of something else, a technological seed released long ago to wander, its instructions forgotten, its function decayed to routine, a device that continues its last command simply because it was built to endure. We might be watching a machine still doing what it was meant to do when our planet was still molten rock. If such an origin were true, how would we know? What evidence could possibly prove intent across interstellar time? In science, we have a saying, extraordinary claims require extraordinary evidence. To prove that Atlas is engineered, we would need more than patterns. We would need material samples showing impossible alloys, or data transmissions that repeat encoded sequences, or maneuvers that defy every known physical law. So far, we have none of that. We have only beauty, coincidence, and curiosity. But the power of this story lies not in its certainty, but in its invitation. It reminds us that imagination is also a scientific tool. Every major discovery begins with someone daring to ask a question that sounds foolish. When the first astronomers proposed that the Earth moved around the Sun, it seemed absurd. When they suggested that stars were suns themselves, people laughed. Perhaps the idea of an interstellar surveyor drifting through our system will one day seem equally ordinary. For now, Atlas gives us something subtler, a living experiment in how we respond to wonder. Do we leap to conclusions, or do we listen longer? Do we cling to fear of the unknown, or do we let curiosity guide us deeper? The very act of asking these questions makes us better listeners to the universe. If the surveyor theory ever proves true, it will not diminish the majesty of nature, it will amplify it. Because to discover intelligence beyond our own would be to realize that the impulse to explore, to observe and to endure is not unique to Earth. It would mean that across the void, others once felt what we feel when we gaze up at the stars, that quiet ache to understand. And if the theory proves false, the story remains worth telling, for it teaches us how to hold the extraordinary and the ordinary in the same hand, and to see wonder in both. Maybe Atlas is only a comet. Maybe it's something more. Either way, it's a mirror, showing us our own longing reflected back from a shard of light moving between suns. Whatever Atlas is, it is doing what all good teachers do. It makes us look closer, think longer, and feel smaller, but in the best possible way. Like seed pods opening, each fragment catching a different angle of sunlight, the mystery of Atlas unfolds not to frighten us, but to remind us. The sky is vast, and possibility is patient. When scientists talk about Through-Eye Atlas now, there is as much philosophy in their voices as there is data. The comet, or probe, or whatever it truly is, has reminded everyone that curiosity can be both a light and a weight. We are drawn toward the unknown the way moths are drawn to flame, but to explore responsibly, we have to remember the difference between wonder and wishful thinking. Science lives in that balance. Every great discovery begins with curiosity but survives only through care. When the radio pulses were first reported, excitement raced ahead of evidence. The word artificial appeared in headlines before the data had even been confirmed. For a few nights, speculation burned brighter than the comet itself, and then the scientists did what they always do. They slowed down, they checked, they tested again. That slowing down is not hesitation, it's discipline. It's the part of science that most resembles meditation. Before a theory can stand, it has to rest in silence long enough to be questioned from every side. A single unverified signal doesn't mean intelligence any more than a flickering candle means a message. The responsible act is to wait, to listen again, and to see whether the pattern endures. Skepticism in this sense is not cynicism. Cynicism closes the door. Skepticism simply keeps it unlocked until proof arrives. When NASA or the European Space Agency say, "No confirmation yet," they are not dismissing the mystery, they are protecting it from distortion. Without that protection, speculation becomes mythology, and the truth, whatever it is, gets lost under the noise of excitement. The principle of extraordinary evidence is not meant to dampen wonder, it's meant to preserve it. It reminds us that believing too quickly is another way of losing the very thing we hope to understand. If Atlas were truly engineered, it would not need our faith. It would reveal itself through consistency, through behavior that resists every natural explanation. Until then, the most loving thing we can do for the mystery is to be patient. This patience, however, doesn't mean indifference. Around the world, teams continue to collect data. Spectra, light curves, and radar echoes are all being shared in open databases so that independent researchers can verify results. Students in small observatories in South America and Eastern Europe are joining the effort, contributing measurements of brightness and colour. The information spreads like ripples from a stone dropped into water, transparent and collaborative. In public forums, some people grow restless with this slow pace. They want answers, not process. But science is process. It's the slow accumulation of confidence, like snow falling softly until the ground becomes white. It's easy to forget that every statement an agency releases has been cross-checked dozens of times, translated into words that minimize misunderstanding. Behind the polished sentences are nights of fatigue, excitement, and quiet debate among people who care deeply about being right, but even more about not being wrong. Avi Loeb, the Harvard astrophysicist whose comments fueled many discussions, once said that the worst mistake science can make is to ignore anomalies just because they seem unbelievable. He is right, but there is a companion truth. To treat anomalies as answers too quickly is another kind of mistake. The sweet spot lies between those extremes. That is where open-minded skepticism lives, the place where imagination and evidence can coexist without war. For the public, participating in that balance means something simple but powerful, learning to follow curiosity without demanding certainty. The best way to honour discoveries like Atlas is not to choose a side, but to keep watching, to ask questions, and to enjoy the act of questioning itself. Science belongs to everyone who looks up and wonders. You don't need a telescope to participate, you only need patience and humility. As December approaches and the fragments of Atlas drift toward their closest pass, agencies are preparing real-time observation feeds that anyone can access. Amateur astronomers will contribute through open networks, turning their backyards into parts of a global observatory. That openness, the willingness to share data to let others check and verify, is what separates science from speculation. It's how wonder becomes knowledge instead of legend. Still, it's worth remembering that wonder has a moral dimension. How we react to the unknown says something about who we are. If we meet every mystery with fear, we shrink the world. If we meet it with reverence, we expand it. Atlas has stirred both reactions. Panic in some corners of the internet, gratitude in others. But perhaps its true gift is teaching us that awe can be steady, that we can marvel without losing composure. The scientists who stay up late tracking its fragments don't talk about aliens or conspiracies. They talk about data integrity, calibration, and the quiet thrill of watching something no one has ever seen before. They measure angles and times, but inside they feel the same wonder as the rest of us. The difference is that they translate that wonder into patience, into method, into evidence. It's their way of loving the unknown responsibly. Maybe that's what science really is, an ethics of wonder, a way of being astonished without being reckless, a way of keeping faith with reality. When we hold that lantern steady, the light we cast is gentle enough not to blind us. Our eyes adjust, details emerge. We begin to see that mysteries are not walls blocking understanding. They are doors waiting for us to slow down and open them carefully. As one researcher wrote in her observing log after a long night, "We are not here to prove, only to notice." That might be the purest expression of what this comet means. It doesn't ask us to decide what it is. It invites us to pay attention. And that attention, that collective stillness, might be the most beautiful part of the entire story. So, as December 19th approaches and the blue traveller glides quietly by, the best thing we can do is what we have always done at our most thoughtful moments. Look up, breathe, and remember that curiosity and caution are not enemies. They are companions holding hands under the same sky. One asks the question, the other makes sure we are ready for the answer. Hold the lantern steady, let your eyes adjust, see more, fear less. The universe is vast, but it is also patient. It waits for us to listen properly. And so, after months of questions, colour and debate, the story of Three Eye Atlas drifts toward its next chapter. Not an ending, but a moment of quiet watching. The fragments that once flared blue near the sun are now on their way past Earth's orbit, gliding in formation through the darkness. Their predicted path will bring them nearest to us on December 19th, 2025, at a distance of roughly 9 million kilometres, close enough for every major telescope to turn its gaze, yet far enough to let us rest easy. There is no threat, only curiosity. As that date approaches, observatories across the world are preparing their instruments. The James Webb Space Telescope will study the fragments' infrared glow to measure their temperature and gas composition. ALMA, in the Chilean desert, will listen for the faint hum of molecules vibrating in the cold vacuum. Radar arrays in California, Goldstone, and Arecibo's successor in Puerto Rico will bounce soft pulses toward the cluster to map their size and density. Each signal will take about 30 seconds to travel there and back, the gentlest game of cosmic echolocation ever played. For ground-based astronomers, the nights leading up to the encounter will be long but calm. Through high-powered telescopes, the 7 fragments may appear as tiny beads of light, their faint tails pointing away from the sun like threads of silk. Even small amateur instruments might glimpse the glow under dark skies, a reminder that the same heavens belong to everyone. While professionals gather spectra and radar reflections, enthusiasts will simply watch. And that too will be part of the science. The story of Atlas has always been about listening together. When we trace its timeline, it feels like a complete symphony. It began quietly on May 7th, when a faint object appeared in archival images from the TESS spacecraft, then about 5 times farther from the Sun than Earth. On July 1st, the Atlas network in Hawaii officially discovered it, the 3rd confirmed interstellar object, after Oumuamua and Borisov. By August, JWST and SphereX had revealed its unusual chemistry, carbon dioxide dominating over water, an inverted ratio that set it apart. Then came the astonishing perihelion of October 29th, when it flared bluer than the Sun itself and swelled to 300,000 kilometres in breadth, 25 Earths end to end. Only a day later came the whispers, those faint radio pulses near 1.4 gigahertz, echoing the hydrogen line repeating in Fibonacci-like rhythm, and by October 31st it had divided gracefully into 7 fragments, their movement so measured that even physicists called it non-ballistic, a phrase as poetic as it is technical. Now, months later, those 7 sparks approach once more, silent but steady, giving us one last chance to watch and to wonder. Each stage has taught us something, even before we know what the final answer will be. The early outgassing showed us that not all comets are built alike. Some wake far earlier than our models predict. The blue emission reminded us that sunlight and chemistry still have secrets to share. The radio murmurs challenged our instincts about pattern and coincidence. And the fragmentation, that quiet unfolding into 7 parts, offered a natural lesson in symmetry, one that doesn't need intention to feel meaningful. As Earth turns beneath it all, the sky will look unchanged to most of us. The news may mention the event, but there will be no streak across the heavens, no sign to the naked eye. The fragments are too small, too far, too subtle. But knowing they are there changes something in the way we see the night. Just as you can feel the warmth of a campfire even when the flames are invisible behind the trees, so too can you feel the quiet presence of something extraordinary moving through the dark, not a visitor demanding attention, but a reminder that we share this cosmic sea with countless travellers we'll never meet. In a way, the story of Atlas has already done its work. It has drawn together the best instruments of a planet, but also the imagination of its people. For months, scientists and poets, skeptics and dreamers have looked up at the same patch of sky and asked the same questions. That unity, brief though it is, may be the most beautiful result of all. The comet, or probe, or fragment of ancient ice has become a mirror, showing us how science and wonder are not opposites but 2 sides of curiosity. One asks what, the other asks why, and both are necessary if we hope to truly see. When December 19th arrives, the data will pour in. The instruments will hum softly as they record spectra, radar echoes and radio silence, perhaps even a faint murmur at the hydrogen line once again. There will be graphs and analyses, but also quiet moments between them. Researchers standing on observatory balconies, gloved hands wrapped around cups of coffee, looking up, half expecting nothing, half hoping for everything. The air will be cold, the stars sharp, and somewhere, a blue traveller will pass unseen, indifferent, yet luminous. Whatever the final analysis shows, whether Atlas is made of exotic ice, whether its signals prove natural or engineered, the outcome will not diminish its beauty. If it is purely natural, then it's a masterpiece of chemistry and chance, reminding us how creative the universe can be without intent. If it is engineered, then we have just glimpsed proof that curiosity itself exists elsewhere, a bridge between civilizations separated by time and light years. And if it remains uncertain, living forever in the space between maybe and almost, then it has done something even rarer. It has kept us wondering without despairing. In the quiet that follows, perhaps we'll understand the deeper gift Atlas offered. Not a revelation, but a rhythm. It taught us to watch more slowly, to listen more carefully, to accept that not all questions must be answered before the night ends. That is the true spirit of the Sleepless Scientist, not racing toward conclusions, but walking softly among possibilities. So, as the blue traveller slips past, you might picture it not as a comet or a machine, but as a thought, one that crossed the long darkness to reach us, burned briefly in sunlight, and then moved on, leaving us a little more awake to the sky. And when you step outside that night, look up. The stars will look the same as they always do, distant, cold, beautiful. But somewhere out there, faintly and silently, a cluster of fragments will be gliding past, each turning in the sunlight, each carrying the memory of its long journey. You won't see them, but you'll know they're there. And maybe that's enough. Because knowing, quietly and without proof, that we are part of something vast and unfinished, that is the most peaceful knowledge of all. So breathe and rest easy. The sky is full of questions, but none of them are here to harm us. They are here to keep us awake in the gentlest possible way. Awake not with fear, but with wonder.